1. Introduction: The illusion of many CPUs. This section explains what a process is and why your computer seems to run many programs at once. You will learn how the OS fakes having many CPUs using just one, and how it splits that work into two layers: mechanisms and policies. What is a process? The process, a running program, is the most basic abstraction the OS gives you. A program by itself does nothing. A program just sits on disk as instructions and static data. The OS reads those bytes and runs them. That act of running turns a program into a process. Think about it. What makes a running program different from a file sitting on disk? Why run many programs at once? Building on this, consider your own computer right now. You might have a web browser, email, a game, and a music player all open. A typical system runs tens or even hundreds of processes at the same time. This design makes the system easy to use. You never worry about whether a CPU is free. You just run your programs. The core challenge: many programs, few CPUs. However, most computers have only a few physical CPUs. The OS must still make each process feel like it owns a CPU. The central question of this chapter is, how does the OS create the illusion of many CPUs when only a few physical CPUs exist? CPU virtualization: faking many CPUs from one. The OS solves this problem through CPU virtualization, sharing one physical CPU among many processes, so each appears to have its own CPU. The OS runs one process, stops it, then runs another. The OS repeats this cycle rapidly. Each process believes it has a dedicated CPU. Think about it. If the CPU switches between processes fast enough, why would each process believe it has its own CPU? Time sharing versus space sharing. The technique behind CPU virtualization is called time sharing. The OS lets each process use the CPU for a short period, then switches to the next one. Many processes share one CPU over time. The trade-off is performance. Each process runs more slowly because processes must take turns on the CPU. In contrast, space sharing divides a resource so each user gets a dedicated portion. Disk storage is a good example. The OS assigns a block of disk to a file. That block stays with that file until you delete it. No one else uses that block in the meantime. Think about it. Why does the OS timeshare the CPU instead of space sharing it? Could you give each process a permanent slice of the CPU? Mechanisms: the how. To implement CPU virtualization, the OS needs low-level tools. The OS calls these tools mechanisms, low-level methods that implement a specific piece of OS work. A mechanism answers the question, how does the OS do this? For example, a context switch, saving one process's state and loading another's, is a mechanism. Think of it like pausing one board game, saving where all the pieces are and switching to play a different game. Policies: the which. On top of mechanisms, the OS needs decision-making rules. The OS calls these rules policies, high-level algorithms that decide what action the OS should take. A policy answers the question, which process should the OS run next? A scheduling policy makes this choice. The scheduling policy considers which process ran most recently, what type of work each process does, and what performance goal the system targets. Think of it like a doctor's waiting room. The mechanism is the ability to call a patient in. The policy decides who gets called next: first come, most urgent, or some other rule. Think about it. Why does the OS separate the mechanism from the policy? What happens if you want to change the scheduling rule but keep the same context switch code? Why separate mechanisms from policies? Separating mechanisms from policies gives the OS modularity. You can swap one scheduling policy for another without rewriting the context switch code. The low-level how stays the same, only the high-level which changes. This separation appears throughout OS design. You will see it again in memory management and file systems. Section Summary. The OS runs many processes on few CPUs by using CPU virtualization. Time sharing lets processes take turns on the CPU. Mechanisms handle the low-level work of switching between processes. Policies decide which process runs next. Keeping mechanisms and policies separate makes the OS easier to change and extend.